In the third part of the cookbooks challenge from the bostonkey.party CTF 2016, we will wrap up the exploit, but let's do a first quick recap on what we achieved in the last video. Okay, so cool. The exploit so far leaked a heap address and then proceeded to use a slightly different bug, but similar, to leak the global offset table entry for printf, which we can use to calculate the libc base address, which will be important later. The next step of the exploit is titled Use libc address to get the free hook pointer. What the free hook pointer is, or generally what a free hook is, we will find out in a second. Let's start another cookbook instance, create a name or anything, just so something is mallocked, attach GDB to it, set a breakpoint to free, and trigger a free from the menu. Now start stepping through the free call. The first thing that is happening is a very small function that is called, which simply moves the value on top of the stack into EBX. If you haven't seen this before, this is just a neat trick to get the current instruction pointer, because when you call a function, the return pointer will be stored on the top of the stack. So if you call a certain function that moves the top of the stack into a register, you get access to the value of the instruction pointer after the function returns. And obviously the return pointer is pointing to free at offset +6, because that is the next instruction after this call. This is useful because, as you know, libc will be loaded anywhere because of ASLR. So if libc needs to calculate some offsets inside itself, it needs often the absolute address. So it uses this trick to get an address which libc then can use to calculate certain offsets to certain places where it wants to. So now that we have the instruction pointer basically in EBX, the next instruction will add a constant 133339A to EBX. Now we can take a look at the memory mappings and we can see where the calculated value in EBX is pointing to, which is another memory area belonging to libc. I'm not 100% sure, but probably like the data segment or something like that from libc. When we step a little bit further, we can see that there's another value subtracted from EBX, hex A0, and that is taken as a pointer, and wherever this address is pointing to has a value stored there, which is then moved into EAX. See this address now in EAX, which has the symbol free hook. And if you look at what the next instruction will do, it will take the value that is stored at this address and moves that one into EAX. In this case, you can see that at this address is stored nothing, it's simply 0. And again, we can look in the memory mappings where this particular address is coming from. And it seems to come from this area that is directly after libc. I have to make clear that I have not that much experience and that I'm a bit unsure what this is, but I can just guess. But I think it's just a memory mapped area that libc did when the program got initialized, which is used for certain variables like the free hook variable. So let's simulate what would happen if a value would have been written there. Let's assume we just had an arbitrary write somewhere and we were able to overwrite this. So this value get loaded into EAX. And then there will be test EAX. So this tests if there was a value set or not. And because we set it now with GDB to 4141, this check is passed. And when we step a little bit further, we can see that eventually we reach a call EAX. So it tries to jump to 41414141, which obviously doesn't exist as a function. So this means that theoretically you could hook free, which means that your function will be executed before free. This is great for debugging purposes, but maybe we can abuse this. If we are able to write any address to this location, we can redirect code execution when we execute free. And the next step of the exploit tries to leak this free hook pointer so that we know where we want to write to in order to hook free. And you can see that I have defined this free hook offset based on the assembler code at the top of my exploit code. For this free hook offset are 3 values defined. Remember that this should be the offset from where libc is loaded. This means that first of all, we obviously have the value that is used in the assembler code, the 1339A. The second value is obviously the offset of free itself. As you remember, the assembler code got the current instruction pointer, which was at 3 + 6. So that is basically this value, which you can see if you look again at the offset from free in libc. the address 76C66. And obviously we still have to subtract hex A0 from that value to get the pointer where the free hook pointer is stored. The same thing obviously has to be also defined for the libc that was provided with the challenge. So to show that off, we can just load the libc that was given with the challenge, and we can look up free there. We can see that it has a different offset, so obviously we have to add a different value there. The other value that we have to know is the value that gets added to EBX, which is also different. And then also whatever is subtracted from EBX and then loaded into EAX has also a different offset. So our first step is to leak this free hook address so that we can write our own values there and thus redirect code execution. So just to make sure that you understand this part, let's do this calculation quickly by hand. So we leak the libc address, obviously. So from that we can calculate the offset to free. The assembler code will get the address of free plus 6 based on how this call trick works. So we can add plus 6 to it, and then we basically have exactly the value that will be gotten from this call trick. And then we add this magic value on top of it, like the assembler code also did, and subtract the hex A0 from it. So this results in a certain address. And the value at this address is the address where we can define a free hook, the address where we want to jump to when we want to hook free. That we know how the free hook offset is calculated, we can also understand the next step. It's exactly the same bug and code that we use to get the value from the global offset table for printf. Just in this case, we calculate a new address based on libc that we have leaked in the previous step. And when we run the code, we can see that this works nicely. After we leak the address from libc, we can calculate the free hook address, as you can see here, and then it will add it to this fake ingredient list, and we get another address that we can leak. So now we know where the free hook address will be. And this works nicely. We are defeating ASLR, and every time we get the different address. The next step of the exploit is called overwriting the wilderness. We want to overwrite the last value on the heap, which says how much space is left in this heap arena. And we want to set this value to FFFF. If we would not set this to a high value and we would try to allocate a very big chunk of data, malloc will try to request a new memory area with mmap from the operating system to have more space available. But if we set it to FFFF, malloc will never think that the heap is low on memory, and basically we can allocate enough values to push the heap forward to addresses where we then can arbitrarily write data to. This technique is often referred to as House of Force. The name for this technique was introduced by a paper called Malloc Maleficarum from, I think, over 10 years ago. There's an updated paper called Des Malloc Maleficarum, which explains some of the techniques and corrects some of the assumptions made and stuff like that. And here it's explaining the House of Force, which is a technique regarding this top chunk, which is the wilderness, the last remaining free heap space. The wilderness is the last chunk, and we don't want to accidentally malloc objects that are in the middle of the heap. So we use fill heap function to fill in all the gaps and defragment the heap, so we know that the new object we create will be at the end of the heap. So now let's do what the exploit code is doing. We start a new cookbook instance and we attach GDB to it. And the first thing is we go into the create recipe menu. Then we create a new recipe with n and we discard it. Let's have a look how the heap looks right now. This is the address of the recipe that we just created. So now we can investigate the heap. Of course the recipe is empty, that's why everything is just 0. But when you look at the 4 bytes before this block, you see the 1FD59, which is the remaining size that is free on the heap. This means that the recipe we deleted was the last allocated block on the heap that we just freed. And if we search the process memory for the address of this free heap space, we find that there seems to be a pointer to that address in memory belonging to libc. So libc is keeping track on where the end of the heap is, where the wilderness begins. The allocation of a new block on the heap can be fairly complex, finding free spots and stuff, but if the heap is filled up like this and you have this pointer into the wilderness, then malloc will simply use this address here to allocate a new block there, because it knows this is the wilderness, this is just free heap, so it can use it. And this pointer obviously has to be updated, because right now it's pointing at this address of the heap. If you would allocate a new block, let's say with 1000 bytes, then this address, this pointer stored in the memory from libc, has to be updated and pushed 1000 bytes ahead as well. Obviously malloc will not allow you to allocate more than one FD59 bytes. But what if you overwrite this with FFFF? Then you could allocate an arbitrarily big memory chunk, which effectively would update and set this address in libc to something different. So if we could allocate an arbitrarily large chunk, we could push the heap into the F75 area of the libc where the free hook is stored. So that's the idea of House of Force. Before we continue with the exploit, let's check one other functionality out which we have actually used before, and that is giving the recipe a name. So in this case we gave the recipe AAA. And if we look at the heap, we can see that the A's are written inside of the receipt block. And again, we have a use after free vulnerability here, because we actually freed this recipe before, but the pointer to it was not discarded as well. So let's continue with the exploit. We go into the add ingredient submenu, and then we allocate a new ingredient with N. When we now look at the heap, we can see that in the area where we previously had the A's written to, there's a different value. So this means that we can overwrite those values with the giving the recipe a name functionality. At this moment I also realized that it was completely unnecessary to create two new ingredients. Delete one is completely sufficient to only create one, because what we want is we want to have the wilderness area starting in the area that we can overwrite with giving the recipe a name. So let's overwrite the size of the last chunk. We should be able to do this with 8 bytes, and then we can set the size. So we go into the create recipe menu, give it a name, and then write 8 zeros and then the FFFs to it. So let's run the exploit code again and look at this on the heap. Okay, so apparently now we should have overwritten this size with FFFFF. So we attach GDB and we look on the heap. Get the address of the last recipe we edited, and then look at this heap area. And we can see that indeed we have written this FFFF, and that should be the start of the free heap area. And we can verify this by searching for the address, and we can find that there is this pointer to this heap area there. Let's move on to the next step of the exploit. Now we want to overwrite this AV top pointer, that is the pointer from libc, to point to an interesting area where we want to write to. Specifically, we want to overwrite the free hook pointer. So we want to point this pointer, this AV top pointer, into the free hook area. Because when we allocate a new chunk, it will be allocated at the address pointed to by this AV top pointer here. And if we point this at free hook, we should be able to create a new object like an ingredient or recipe and then write to this location. So first of all, we need the address of the current wilderness. And we have leaked the heap address before, and because the heap is deterministic when allocating new stuff, we know that at the offset 4458, which is the start of the wilderness. This is important because we have to malloc a specific size to push this AV top value pointer further ahead to the area that we want to. So we have to carefully calculate that one. Okay, so let's verify that we get the heap wilderness address correctly. We can run the exploit and then look at it in GDB. Okay, now we should have overwritten the wilderness with FFFFFF. And we can take the calculated offset and check it out in GDB. And we can see that we have successfully calculated the location of the wilderness and also changed it to all Fs. Next, we have to calculate a magic malloc value that will push the AV top pointer to the free hook area. So let's get the current wilderness pointer. And luckily the cookbook has the functionality to malloc a block with the size that we specify. This is the give the cookbook a name feature where it asks us how long the name should be, and that will simply malloc this size. So that's perfect. So at this address we can find the wilderness. So how much should we allocate that we can move this forward to the area of free hook? So obviously we have to calculate the offset between the current heap wilderness location and where we want to write to, or a little bit before the area where we want to write to. So just take the location you want to reach and subtract from this value the current heap wilderness address. So we can run the exploit and take the magic malloc value that was calculated by the exploit and verify this by hand. We can see that this new block that was allocated has the size of EE0 something. If we add to this now the address from the previous wilderness function, we should reach the area where we have the free hook. Check where free hook is again. We can simply take the output from the exploit. And we can see that it's at 8D8 and the area that we have calculated is at 8Z0. So we are just a little bit before the free hook area, which is great because the new area that we malloc would be exactly in this area. But thinking about it again, I have decided to move the new free area a little bit closer to the actual free hook, which makes it easier with the functions that we can use. I have decided I want to overwrite this free hook with the address of system because that can easily execute a shell. And we can easily do this by just giving the cookbook a name, which will allocate a new chunk, and then we can simply write the address, which we can calculate from the libc base address plus the offset from system, depending on which libc you're using. So when we run the exploit to the step where we overwrite the free hook with system, we can check this fact in GDB. So this is the free hook address, and then we can verify that this address here is indeed system. And again, the address of system can be calculated because we know the libc base address and we know the offset of system inside of libc. So now we are almost at the end of the exploit. We have overwritten the free hook pointer with system, so every time when we free an object, we will call system. And there's a cool trick how we can utilize this, in this case for the cookbook. Basically, we can give our cookbook a name, and luckily everything will just fall perfectly into place with reading the cookbook name like this, because the stack and everything will be perfectly prepared for the system call. So the idea is that we give the cookbook a name, we write in this command we want, and then we free the cookbook name again, which will trigger system and it will execute the command that we have specified. To visualize this better, let's quickly change the exploit and put this cool trick in there so we can get control over the menu again. So we run through the exploit and now we can write our own commands again. So let's try this. Let's give the cookbook a name, which is a command we want to execute. So G and just an arbitrary length, doesn't matter. And then for example, ID. And now when we free it, we will call system. Boom, there it is. We executed ID and we can see the output of the command. So why does this work? Why does this work when we type in a command like this and then we would free it with R? So let's have a look again at the remove cookbook name function in IDA. So we can see that it takes the pointer where we have written the name to and stores it in EAX and then calls free. Because free takes the pointer to the buffer that was allocated as a parameter. And system also takes one parameter in EAX, which should be an address pointing to the string that should be executed. That's pretty convenient. So when we press R, we will execute uname -a. And obviously we can wrap this in a nice loop. We always ask the user for some input, which we then create a new cookbook name for it, and then we remove this cookbook name to trigger system and execute this command. And it looks pretty neat. Very proud of it. And again, down here, here's the output of the actual server during the CTF challenge. So before we end this 3-part adventure into heap exploitation, thank you very much for watching. I hope you have learned something. I have definitely learned a lot from this challenge. As I mentioned in the very beginning, this was a little bit over my skill level, and during those hours and hours I've spent on this, I have learned a lot. And I'm deeply, deeply sorry if I accidentally used the wrong terminology for stuff. I'm still not 100% sure if I have understood what exactly the wilderness is and stuff like this. So just keep that in mind. But anyway, what matters is the technical details. What matters is how it's actually done and how the exploit works. That is the proof of concept. The actual name doesn't really matter. It's just semantics. So see you next time.